very important for the study of transmission line. Now, Smith chart is nothing but a transformation of normalized impedance to complex gamma plane. What is gamma? It's reflection coefficient. So complex gamma plane. We know that the gamma, the maximum value of reflection coefficient is 1, and okay, before that, normalized impedance. So we know that any impedance divided by characteristic impedance is called as the normalized impedance. So in general, Z bar is given by Z divided by Z naught. So this is equal to, in general, I'll call this as R plus JX. So in general, any impedance is resistive plus resistance. Any impedance is sum of resistance plus reactance. Here, this R is normalized resistance, whereas this X is normalized reactance. So in Smith chart, we are going to use normalized impedances, not the normal impedances. Now, what we are going to do is we are transforming the normalized impedance into complex gamma plane, and also the maximum value of gamma is it's less than or equal to 1. So mod of gamma is less than or equal to 1. Okay. Now we have Z bar is equal to R plus JX, and also in terms of gamma we have a relation that Z bar is 1 plus gamma divided by 1 minus gamma, because we know that we have seen that gamma is in general Z minus Z naught divided by Z plus Z naught. This relation we have already obtained. Now this, from this equation you can find the value of Z, and then you can find the value of Z bar. So here itself you can make it as Z bar. So first of all, so tau can also be written as, just divide this by Z naught. Divide this entire equation by, in the numerator and denominator, by Z naught. You will get Z bar minus 1 divided by Z bar plus 1. So just cross multiply and get the value of Z bar. You will get this. Okay. So what we are doing is we are transforming normalized impedance into complex gamma plane. Now let me assume that the axis in complex gamma plane are U and V. The axis in complex in the impedance plane is nothing but R and X, whereas in complex gamma plane I am assuming gamma is U plus JV. So therefore I can write this as R plus JX is equal to, in place of gamma I can write U plus JV divided by 1 minus U minus JV. Now we need to rationalize this. Now we rationalize this and we equate the real and imaginary terms. So what will happen? So rationalizing the above equation and equating real terms. So first what we are doing, we are equating only the real terms. So when we equate the real terms, I'll get an equation U square minus 2 into R by R plus 1 into U plus V square plus R minus 1 divided by R plus 1 equal to 0. So we will get an equation, and this equation is a equation of circle. This is a circle equation whose center is given by center is r by r plus 1 comma 0 and whose radius is 1 by r plus 1. So we have got this equation when we have equated the real terms. Now when we equate the imaginary terms, on equating imaginary terms, we'll get u square plus v square plus minus 2u minus 2 by x into v plus 1 equal to 0. Now for this case, the center is 1 comma 1 by x and radius is 1 by x. Fine. So these circles, when we have equated the real terms, these circles are called as constant R circles. Whereas on equating the imaginary terms, we have got a set of circles, and these circles are called as constant X circles. So constant resistance circles and constant reactance circles. Now let us study the constant resistance circle first. So on one side of this table, I have divided the page into two columns. One is constant R circles, and on the other side I will study the constant X circles. Now so constant R circles have center at, so their center is r by r plus 1 comma 0 and their radius is and their radius is 1 by r plus 1. Now first of all, r equal to 0. So for r equal to 0, the center is 0 comma 0 and radius is 1. So this circle will be like this. So this is R0 circle. Its radius is 1 and its center is 0 comma 0. Then next, for r equal to 1, we have center at 1 by 2 comma 0 and radius is half. So this is 1 by 2 comma 0 point and radius is half. So this circle will be like this. This is r equal to 1 circle. R equal to 1 circle. Next, as you keep on increasing the value of r, as you go on increasing the value of r, what will happen? The radius of the circle will keep on decreasing and the center will keep on shifting towards the right side. So you will get the circles like this. So what are the characteristics of constant R circles? The first thing is, all the constant R circles have their center on U axis. This is U and this is V. So their their centers are lying on the positive u axis. It starts from 0, 0. Yes, for r equal to infinity, what will happen? Radius will be 0 and center will be at so r equal to infinity. So in that case, center will be at 1, 0. So therefore, it is a point circle because radius is 0. For r equal to infinity, radius is 0. So therefore, it is a point circle. So this is r equal to infinity. So constant r circles, what all the constant r circles have center on positive u axis. All the circle passes through 1, 0 point. This is 1, 0 point. And as you increase the value of r, what will happen? The center will shift towards the right and radius of the circles decreases. These are the characteristics of constant r circles. Now concentrate on constant x circles. Okay. So constant x circles. So constant x circles have so their center is their center is 1, 1 by x and their radius is 1 by x. Now for x equal to 0, the center is 1, infinity and radius is also infinity. What is the meaning of infinite radius circle? So infinite radius circle means a straight line. And since its radius is its center is 1, infinity, so it is a straight this axis, this is nothing but x equal to 0 circle. This real axis is nothing but x equal to 0 circle. Now next, x equal to 1. For x equal to 1, the radius is 1. Now x can be either positive or negative because it is reactance. So reactance can be positive or negative, but resistance is always positive. So therefore we did not consider negative values while studying the constant r circles. But while studying constant x circles, we need to consider negative values also. Now for x equal to 0, what is happening? For x equal to 0, the center is 1, infinity, whereas radius is infinity. Right? So this x equal this straight line, this our imaginary axis is nothing but the real axis is nothing but x equal to 0 circle. Now next, x equal to 1. For x equal to 1, the center is 1, 1 and radius is also 1. So center is 1, 1 and radius is also 1. So therefore it would be a circle, this circle. Its center is 1, 1. Similarly, for x equal to -1, what will happen? Center is 1, -1 and radius it's coming out to be -1, but in general radius is positive. So therefore it will be a circle, this one, the opposite circle, 1, -1. Now for x equal to 2, what will happen? So you observe that all the centers will lie on this u equal to 1 line. This u equal to 1 line will contain all the centers. All the circles have their center on u equal to 1 line. Now and as you increase the value of x, the radius keep on decreasing. First, initially for x equal to 0, the radius was infinity. For x equal to 1, the radius has become 1. Now as you increase the value of x, the radius keeps on decreasing. Next, for x equal to infinity, what will happen? For x equal to infinity, the radius center will be 1 comma 0 and radius is 0. So again it is a point circle which lies on 1 comma 0. So now what are the characteristics of constant x circles? Circles represent the positive reactance, whereas the circles in the lower half, they represent the negative reactances. Again, as you increase the value of x, the radius decreases and the centers of circle shifts towards the point of 1 comma 0. So these are the characteristics of constant x circles. These are very important because these constant r circles and constant x circles, when they are combined, it forms the complete Smith chart. So the Smith chart is nothing but the combination of constant r circles and constant x circles. So I have explained you the entire process of how we have obtained the constant r circles and constant x circles. Whatever we are studying, this is nothing but our constant gamma plane. Remember, this is constant gamma plane, and we are transforming the normalized impedances to the normalized impedance to complex gamma plane. Now, based on the constant r circles and constant x circles, we will define few important points on the Smith chart. So this is u axis, this is v axis. This is r0 circle, r equal to 0 circle. We know that this real axis is nothing but x equal to 0 circle. Let me draw a bigger circle over here. Okay. So, okay. Now, what this point denotes? This is the intersection of, so this is r equal to infinity and x equal to infinity. We have already seen this is 1 comma 0 point. So here they converge. Fine. Then this is the intersection of, this point is r equal to 0 as well as x equal to 0. Here we know that there is a small r equal to 1 circle. Let me draw that, and let me draw 2 more circles. So this is r equal to 1 circle, this is x equal to 1 circle, and this is x equal to minus 1 circle. Okay. Now, what does this point denotes? This point denotes r equal to 1 and x equal to 0 circle. This is r equal to 1 and x equal to 0. This point denotes r equal to 0 and x equal to minus 1. And this point denotes r equal to 0 and x equal to 1. So these are few very important points. Now what is the meaning of R equal to infinity and X equal to infinity? Here the impedance is infinite, and impedance infinite means it is open circuit. Now R equal to 0 and X equal to 0 means it is short circuit. R equal to 0 and X equal to 1 means positive reactance, that is inductive reactance. Inductive, this particular upper half of the circle, this denotes upper half of the Smith chart, it denotes the inductive reactances, whereas lower half of the Smith chart denotes the capacitive reactance, because all the reactances are negative. Next, so these are the important points on this Smith chart. Next we will study the there are one more type of circles, and they are called as constant VSWR circles. These circles are not actually present on the Smith chart, but they are needed in order to analyze the Smith chart. So the circles which are actually present on the Smith chart are only constant R circles and constant X circles, but we need the in order to find few quantities or few unknown variables, we need the constant VSWR circles also. Now we know that reflection coefficient tau of L, that is reflection coefficient at any distance L, is tau L, that is load reflection coefficient, into e to the power minus j beta L. This we have already j2 beta L. We have already seen this, where tau L is nothing but load reflection coefficient. Now in general, the load reflection coefficient is also complex. So tau L is also complex in general. Tau L is also complex in general. So therefore, I can write tau of L as mod of tau L into e power j theta L. So I'm just converting into the polar form. I'm just writing it into the polar form, magnitude at an angle of theta, into e power minus j2 beta L. And this can be written as mod of tau L into e power j theta L minus 2 beta L. Now, this mod of tau L represents the radius, and theta L minus 2 beta L represents the, now this is a circle. This represents a circle. If we increase the value of L, then what will happen? What will happen? This will become more negative. That means so this represents a circle. In this circle, the radius is mod of tau L, and this angle is theta L minus 2 beta L. This is called as a constant VSWR circle. Because why this is called as constant VSWR circle? Because we know that VSWR is 1 plus mod of tau L divided by 1 minus mod of tau L, and for a circle its radius is constant, and its radius is constant means mod of tau L is constant. So therefore it is a constant VSWR circle. So if you increase the value of L, it will move in the anti-clockwise direction. So therefore, and what is the meaning, physical significance of L increasing? We have already stated in the beginning that L implies that L equal to 0 implies the load end, and as you increase the value of L, you are moving towards the generator. So therefore increasing L implies moving towards the generator. This is very important. Moving towards the generator. If you increase the value of L, you are moving towards the generator. And so that means moving on the Smith chart in anti-clockwise direction means you are moving towards the generator. Whereas reverse direction means you are moving away from the generator. So this is all about constant VSWR circles. So I hope this is understood why these are called as constant VSWR circle, because on this circle the VSWR is going to be constant, because the tau L, the reflection coefficient, its magnitude is going to be constant, and the magnitude is nothing but the radius of the circle. So the radius of the circle is going to be constant, and hence the VSWR is going to be constant. So this 2 beta L term is responsible for the movement on the VSWR circle. Next, let us look at the characteristics of constant VSWR circle. So the first characteristic is the center of all VSWR circle is origin of this complex gamma plane. The origin is nothing but the center. Then mod of gamma L equal to 1 is maximum value. Yes, this is also sure, because the maximum reflection coefficient value can be 1. It cannot be greater than 1. So the radius, if the radius of VSWR circle is more, it means the given transmission line is having worst match. So large radius implies large reflection coefficient, which implies worst match. That means load and the characteristic impedance has large difference in the impedance. So these are the few important terms about the transmission line. Now, where can we use? So we can do the transmission line calculations very easily with the help of Smith chart. So let us look that how the Smith chart will help us in order to do the calculations. So transmission line constant. So this 2 beta L term, given transmission line is having worst match. So large radius implies large reflection coefficient, which implies worst match. That means load and the characteristic impedance has large difference in the impedance. So these are the few important terms about the transmission line. Now, where can we use? So we can do the transmission line calculations very easily with the help of Smith chart. So let us look that how the Smith chart will help us in order to do the calculations. So transmission line calculations. So first is we can find the load reflection coefficient. So with the help of Smith chart we can find the load reflection coefficient. So if load is given to me, I can find the load reflection coefficient very easily with the help of Smith chart. So first of all, load will be given to me, load value. So what I'll do is I'll plot the value of load. So suppose this is my Smith chart. So what I'll do is a load will be given to me. Suppose this is the load. This is R plus Jx. This is point P, which denotes R plus Jx, suppose. Now what we will do is we will measure the distance of this point P from the center. This distance. And this distance is nothing but the mod of tau L. We know this. This distance OP. This distance OP is nothing but mod of tau L. That is the magnitude of reflection coefficient. Now we have to find the reflection coefficient, and in general reflection coefficient is nothing but it is complex in nature. Now this angle, this theta L, we will measure this angle. That is the angle which this OP makes with respect to positive U axis is called as theta L. So therefore tau L in general will be mod of tau L into e power j theta L. This is how you can find the load reflection coefficient. Then second, reflection coefficient at a distance from the load. So how will you find the load reflection coefficient at a distance L? Now we have already seen that the movement on Smith chart is because of 2 beta L term. Fine. So now first of all a load will be given to me. So I'll plot that load. So suppose this is my point P, which is R plus Jx. And afterwards we will draw the constant VSWR circle, which we can draw with this as the radius. This is my mod of tau L. So with this radius I'll draw the load reflection, I'll draw the VSWR circle, constant VSWR circle. Now so we know that the movement on Smith chart is because of the 2 beta L term. That is theta L minus 2 beta L is nothing, is the movement on Smith chart. This is theta L. This is theta L. Now what we have to do is we have to move away from the generator. We have to move away from the load, sorry, or towards the generator. So as we increase the value of L, this 2 beta L term, this will increase, and therefore we will move on the Smith chart on this side. Suppose after moving 2 beta L, I reach here. So my new theta L is this. This is my new theta L. Let me consider this as theta L dash. So therefore the new reflection coefficient at a distance L is, this is because of the movement L. So therefore the reflection coefficient tau L dash is mod of tau L, because the magnitude of tau L is not going to change. What will change? Only the angle will change. So therefore the magnitude of tau L will remain same. The only change will be minus j theta L dash, sorry, plus j theta L dash. So in this way we can find the load reflection coefficient at a distance from the load. So we are moving towards the generator and we have found the new reflection coefficient. Next, what else can we do? We can find the transformed impedance at a distance from the load. That means we know the load value at load value. Now at a distance L, I can find the value of impedance using the Smith chart very easily. Now this can be done. This we have already done in this case itself. So what we are doing? We are finding the transformed impedance. Transformed impedance at a distance from the load. So this till this point you have to repeat. This point is Q, suppose. So what you will do is, first of all you will plot the given impedance, and then you will travel a distance L. So for that you will find 2 beta L value, and you will subtract the value from theta L, and you will get the new point Q, and the new point Q will give you an intersection point of R and Jx. That particular impedance will be the transformed impedance. The impedance at Q will be the transform. So this R dash plus Jx dash will be the new impedance. So it is very easy to find and by procedure, by equations, you need to use the impedance transformation relation, and then you can find the load, the value of impedance at any distance L. Then you can find the value of VSWR directly. VSWR on the line. You need not use any equation at all. Directly by using the Smith chart, you can find the load, the value of VSWR. Now for this case, we need to understand. Okay, we know that the R max value, that maximum impedance on the Smith chart is rho into Z naught. We have seen this, and since we are plotting the normalized impedances, so therefore I can write R max is R max divided by Z naught. It is nothing but rho. So therefore, if I can find the value of maximum impedance on the Smith chart, R max value, then that value itself is nothing but the value of VSWR. Now on Smith chart, this is constant VSWR circle. So this is constant VSWR circle, and we know that if you remember the constant R circles, so the value of R keeps on increasing as you move towards the right side. So therefore, remember that this point represents the value of R min, and this point represents the value of R max. Because if you observe the constant R circles, what was happening, as we were increasing the value of R, the center was shifting towards the right. So therefore, this represents the R max and this represents R min, and R max is nothing but rho, the VSWR. Now this is how you can directly find the VSWR on the line. So this point, this value itself will give you the, once you draw the constant VSWR circle, then the value of R max will give you the VSWR value directly. Next, you can find the location of Vmax and Vmin using Smith chart directly. So you know that R max will give you the position of Vmax. Wherever you have maximum resistance, there you will have maximum voltage. So therefore, the position of R max itself is nothing but Vmax. So this is the location of Vmax, and this is the location of Vmin. Reverse is the case for Imax and Imin. So R max implies Vmax, R min implies Vmin. And finally, this is very important, identifying the load. A question in GATE question is being asked on this topic, on this particular topic. So please understand this carefully. Identifying the type of load. So by looking at the VSWR pattern, the standing wave pattern, you can easily recognize what type of load it is having, what kind of load is connected to the transmission line. Now, for inductive load, now suppose this is my Smith chart. Let me consider one circle. You know that all these points represent the inductive reactance. Now, if the load connected is R plus jx, suppose, so then where will you locate R plus jx? R plus jx will be located somewhere on the positive half side. It means on the upper half of the Smith chart. Now, when you increase the value of, when you move towards the source, when you move towards the generator, what will happen? First of all, you will obtain Vmax. This point is Vmax and this point is Vmin. So when you will move towards, when you increase the value of L, that means you are moving towards the generator. First you will obtain Vmax, then you will obtain Vmin, and then you will obtain Vmax, Vmin, and so on. So therefore, for R plus Jx type of load, what will be the type of VSWR pattern? What kind of VSWR pattern will be generated? So this will be, so first Vmax will be generated, and then Vmin, then Vmax, Vmin, Vmax, Vmin, and so on. So this is Vmax and this is Vmin. So this is mod of V. So this is for R plus Jx. If the load is R plus Jx, then this will be the VSWR pattern, standing wave pattern. This is load end, and this is increasing L. Next, if the load is R minus Jx, then the point will be located in the bottom half of the circle, bottom half of the Smith chart. And when you move towards the generator, you will obtain Vmin first. So you will obtain Vmin first in that case. So this will be the VSWR pattern for this is Vmax and Vmin. This is R minus Jx. So when you move towards the generator, so as you increase the value of L, first you will obtain Vmin and then Vmax. Now for purely resistive load, what will happen? So purely resistive load means x equal to 0. So we know that this is nothing but x equal to 0 circle. So all the purely resistive loads will lie on this real axis. Now we know that the center point, I forgot to mention this, I should have mentioned this earlier when we were studying the important points on Smith chart. Just let me go through this one. Yes, this point is very important. What does this point indicate? This is R equal to 1 and x equal to 0. What does this mean? This means that R equal to 1 means it is actually R divided by Z naught equal to 1. That means R equal to Z naught. What does this mean? This means that you are connecting a matched load. This is matched load condition. So this is matched load. Here the R is equal to Z naught. Now you can coming back to this point. Now I am talking about the purely resistive loads. So now if the load connected, if the R connected is greater than Z naught, then it will be Vmax. So it will be at the Vmax. And if the resistance connected, if the load resistance connected is less than Z naught, then it will be at Vmin. So therefore, in this case, the VSWR pattern would be, so when the R is greater than Z naught, it will be like this. This is for the case when R is greater than Z naught. And similarly, the opposite of this will be for R less than Z naught. So this is for R less than Z naught. So in this case, you will get Vmax first, Vmax, and this is, in this case, you will get Vmin. So we have considered three types of load: the resistive load, the inductive load, the capacitive load, and the resistive load. Now let us look at the short circuit load and the open circuit load. So if the load is short circuited, then we know that this point, this Vmax point itself denotes the short circuited load, and therefore you will obtain Vmax first. But what is the difference between a purely resistive load, a purely reactive load, and the load with the inductive, this R plus Jx? That means if I have purely inductive load, that is only Jx, and this R plus Jx, what will be the difference between two? So the difference will be, for R plus Jx, the Vmin is not 0, whereas for the purely reactive case, the Vmin value will be 0. Why? Why it will be 0? Because, yes, let me explain this. This is very important actually. This must be understood. So yes, what is VSWR? So VSWR is 1 minus mod of tau L divided by 1 plus mod of tau L. Now, what is tau L? So tau L is ZL minus ZL plus ZL minus Z naught, ZL minus Z naught divided by ZL plus Z naught. Now, for purely reactive case, ZL will be Jx minus Z naught divided by Jx plus Z naught. Now I need the value of mod of tau L. So what will be the value of mod of tau L in this case? So if I find mod of tau L, it is nothing but 1. Mod of tau L will be 1. And therefore, the reflection, this is 1 plus tau L divided by 1 minus tau L. So mod of tau L is 1, so therefore reflection coefficient will be, VSWR will be infinity. And VSWR is actually Vmax divided by Vmin. So what is happening actually, when the purely reactive load is connected at the load end, then there is no one to absorb the energy, and therefore this is the case of full reflections. So when purely reactive load is connected at the load end, the entire wave the entire voltage will get reflected back. The entire wave which is traveling in the forward direction will get reflected back. So therefore, you will have maximum reflections. That means the tau L value is 1 and VSWR value is infinity. And VSWR infinity, when the VSWR infinity is possible, when V min is 0. So therefore, for purely reactive case, the V min value will be 0, which is not in the R plus JX case. Now, so there is not much difference between a purely reactive load and a uh, and a R plus JX type of load. So first let me consider purely purely inductive load. So for purely inductive load, what will happen? Purely inductive case. So let me draw the Smith chart again over here, just a diagram of Smith chart. So purely inductive load means it will lie on R equal to 0 circle. So R equal to 0 means resistance is 0, and now upper half of this denotes the inductive load. So the load which is on the upper half is Jx now. So it is purely inductive. So we will obtain Vmax first. So therefore it will be like this. This is Jx load. Purely inductive load. This is Vmax and V min is 0. So this is plus Jx. What about minus Jx? So in minus Jx case, you will obtain the V min first, like this. So this is Vmax and you will receive V min which is 0. So this is minus Jx case. Now what about short circuit load and the open circuit load? So short circuit load, if the load is short circuited load directly appears on the Vmax. So therefore at the load end itself you will have Vmax. So for short circuit load you will have Vmax directly and you will have the pattern like this. Again, short circuit load is a full reflection case, whereas for open circuit load, this is the pattern. This is the VSWR pattern. So by looking at the VSWR pattern, you can easily recognize what type of load is connected to the transmission line. Now, based on this, there was a question. So let us solve that question. The question was that VSW pattern in a lossless transmission line with Z0 equal to 50 and a resistive load is shown in figure. This is 1, this is 4, This is lambda by 2. This is lambda. This is Z. Now the question is the value of the load resistance is. So the first part of this question is I have to find the load resistance. Now look at the VSWR pattern first. So V minimum in the problem itself it is given that the load connected is a resistive load. Also the characteristic impedance is given to me. Now when resistive load is connected, it is either Rmax or Rmin. This is for sure. Now we have to decide whether it is Rmax or Rmin. Now if you observe the VSWR pattern, so this point is lambda by 2. So obviously this point is the load end, because for every lambda by 2 distance we know that the impedance value repeats. So therefore if this is lambda by 2, this must be the load end. So this is load end. Now if you observe the VSWR pattern, the V min is occurring first. V minimum is occurring first. At the load end, V minimum is occurring. And since the V minimum is occurring first, therefore this must be R minimum. So the answer of this is, the solution of this is, since V min is occurring at the load end, the load connected must be R minimum. And how can you find the value of R minimum? So R minimum is Z0 divided by rho. This is known to us. Now how will you find rho? So rho is Vmax divided by Vmin. What is the value of Vmax? Vmax is 4 divided by 1, so 4. So the value of Rmin will be equal to 50 divided by 4, which comes out to be 12.5 ohms. So this is the value of load resistance connected. Now the second question is the reflection coefficient. So what is the value of reflection coefficient? You have to find out. Now we know that the reflection coefficient is rho minus 1. This is the magnitude of reflection coefficient. So this is 4 minus 1 is 3 divided by 5. It's 0.6. Now we know that tau L is, or else you can directly find tau L by making use of this relation. Instead of going through this relation, now you need to again find the angle, because you have just obtained the magnitude. Okay, so what you do is you directly use the relation of tau L is ZL minus Z0 divided by ZL plus Z0. You will get the answer directly. So what is the value of ZL? It is 12.5 minus Z0 is 50 divided by 12.5 plus 50. If you solve this equation, you will get the answer as minus 0.6. This is actually minus 37.5 divided by 72.5. So just solve it with the help of calculator. You will get the answer as minus 0.6. So in this way, you can use the transmission line in order to obtain the type of load connected. Just by looking at the VSWR pattern, you can. This is GATE 2005 question. This is a linked question which has appeared in GATE 2005. So this Smith chart is also very important, and it's very easy actually. You need not even use the Smith chart in the exam. You just need to understand the concept of Smith chart and you have to apply it over there. We will see few